if heat is transferred between two objects that maintain a thermal equilibrium, what is the entropy change? There's no numbers here. So are we going to do a calculation? Well, let's check this out. So if I draw a sketch, it just represents arbitrarily two objects. Doesn't really matter what shape they have. But I'm going to say this is object 1. And here in thermal equilibrium with it is object 2. And let's say that there is heat flowing from object 2 to 1, but they are in thermal equilibrium. So this arrow represents a Q, but they are both at the same temperature T. And so based on that, if I calculate the change in entropy for object 1, that will be equal to Q over T. If I calculate or write an expression for the entropy change of object 2, since object 2 is simply exchanging heat with object 1 or heating it up, really object 2 has an overall amount of heat that's equal to minus Q as defined in the picture. And so based on that, the overall entropy change for this situation is the sum of these two, which, since those two, one of them is Q over T and the other one's really minus Q over T, those are equal and opposite, so they clearly cancel each other out, which yields a net entropy change of 0. And this winds up being a general result that for reversible processes, the entropy change, if you track all entropy changes, will be 0. So this example is just one example of a reversible process, but it turns out that holds for all reversible processes. In the last example, I'd said that for an irreversible process, if you track all the entropy changes, it will be positive. Another way you can say what I'm saying in these two examples is that for a closed system, the entropy change will be 0 or positive. It can never be negative. If it's 0, it means you're describing a perfectly reversible process, again, in a closed system. And if it's positive, it means it's an irreversible process in a closed system. And saying closed system is another way of saying you've tracked all the associated entropy changes. If you don't say it's a closed system, it means there might be some entropy change that's caused by the process you're describing that is outside that system. And it is possible to have entropy changes that are negative. In fact, I think one of our early examples, we had a negative entropy change. I think it was a second example. But that was because we were considering really only part of the process, or moreover, we could say the system was defined in such a way that it wasn't closed. So if you go away from this and say, hey, entropy can never be negative, it's really contextual. It depends on what your system is. Is it closed, and or are you tracking all the associated entropy changes with the process that you're considering? So I've put the answer up here, and you can see it says 0, and note that this is an example of a reversible process.